Okay, we're continuing with 7.1 notes. Again, just to run through the steps. When we're given our two graphs, we're always going to be finding the intersection between those two functions by setting the equations equal to each other, solve for x. When we solve for x, we're going to achieve our left bound and our right bound that we need for our integral notation. We're going to identify the top graph and bottom graph. Something I left off here is we want to kind of shade in that region that we're dealing with so that we don't get thrown off by maybe the x-axis or y-axis that's somewhere in the middle, because we don't want to pay attention to other lines or other parts of the graph that is not our part of our outer boundaries. So even though we see the x-axis here, that's not part of the boundary, because the boundary is simply between the two curves, the parabola opening down and the parabola opening up. And the next thing is, after you identify that shaded region, you're going to draw a representative rectangle that's going to connect from one end of your boundary to the other end of the boundary. So it doesn't matter where you draw the rectangle, as long as you connect from one end to the next. And this is as a visual assistance so that we can identify what is the top function and what is the bottom function. So the top function is simply whatever the top of the rectangle is touching, that's going to be your top graph. And then whatever the bottom of the rectangle is touching, that's going to be your bottom graph. Okay. And then once we have our top graph and bottom graph, then basically our work is pretty much done. We just have to put it into a formula. Make sure you close off your bottom graph with a set of parentheses, your left bound followed by upper bound, and then the rest just goes in your calculator. Okay, so let's walk through number 3 here. Okay. So the first thing is we're going to find our bounds, and as we find our bounds, we set our two equations equal to each other. Okay. Next step, we're going to try to bring everything over to one side, so I'm going to add x squared to both sides, subtract 2x, and subtract 3. Okay, so the next step I get is 2x squared minus 6x equals 0. I can factor out a 2. When I factor out a 2x, I get an x minus 3. I set the 2x equal to 0. I set the x minus 3 equal to 0. 2x equals 0, so that's x equals 0. Set the x minus 3 equal to 0. I get x equals 3. So those are our bounds. Okay. After we draw our after we shade in our shaded region, our boundary region, and we draw our representative rectangle, we know that the top graph is sitting on this curve, and we know that this curve is the negative x squared, because negative x squared, if we just think about what we know about just some basic family functions for quadratics, negative x squared is always going to be a parabola opening down, right? And positive x squared is going to be a parabola opening up. So positive x squared, negative x squared. So even though we may not know the exact location, we know that the shape of the graph that corresponds with x squared and with negative x squared, and that will allow us to conclude that this curve that opens down must be the negative x squared. So we have our top function and bottom function identified. The top function is the negative x squared plus 2x plus 3 minus big parentheses. We fill in the bottom function into this set of parentheses, and the rest can go in our calculator once we have our bounds in place, using the TI-84, using the 36 Pro, or the online calculator, which you can just search in Google. Okay. Either way, we should be able to get our area of 9 square units. Okay. All right, number 4, same idea. X squared plus 2x and x plus 2. We have the graph shown. Shaded. We identify that shaded region. We connect the distance between the one boundary to the next. We set the two equations equal to each other. Bring everything over to one side. Subtract the x to the left side, subtract the 2 to the left side, and 2x minus 1x gives us positive 1x. We factor, multiplies to be negative 2, adds up to be 1, ends up being plus 2 and negative 1. Solve for x, we get negative 2 and positive 1. Those are our left bound and our right bound. The top graph is sitting on the linear graph. The linear graph is the x plus 2. And the parabola, the curve, is the x squared plus 2x that opens up. So top graph is x plus 2 minus the bottom graph, which is parentheses x squared plus 2x. And the rest can go in our calculator. Area of 4.5. We can convert that to a fraction, but either form is fine. Okay, number 5. Find the area between the two graphs. We have negative x squared plus 3x plus 1. That's the parabola that's opening down because of negative x squared. The negative x plus 1, that's the line with the negative slope, the negative x. We identify that shaded region. We connect that distance with a representative rectangle. Top function is negative x squared. Bottom function is negative x plus 1. We find our bounds. Bring everything over to the left side. Add the x squared. Subtract the 3x. Subtract the 1. We get x squared minus 4x equals 0. Factor the x out. We get x times x minus 4. When we solve for x, we get x equals 0 and x equals 4. And then we're ready to plug into our definite integral. Top function gets entered first. Minus big parentheses, followed by the bottom function. Enter in our calculator, 32 over 3 square units. All right, number 6. Negative x squared plus 4x plus 5 is the parabola that opens down. X plus 1 is the linear graph with a slope of 1. We set the two equations equal to each other. Bring everything over to one side. Factor, multiplies to be negative 4, adds up to be negative 3. That's negative 4 and positive 1. Solve for x, we get 4 and negative 1. And then we're ready for our definite integral area formula. From negative 1 to 4, top function, minus big parentheses, bottom function. The rest goes in our calculator, 125 over 6 square units. Okay, these last two are a little bit different in the sense that if we look, the area now spans across two separate regions. And one thing that we notice is that a top graph and bottom graph relationship in one region is not quite the same in the other region. All right, there is an alternating or flip-flopping effect that occurs from one region to the next. So this curve, this 3x cubed minus 3x, it doesn't remain as the graph on top all the way through. All right, for this first left region it does, but then as we move to the region on the right, it suddenly transforms to being the graph on the bottom. So because the top function and bottom function alternate between two regions, we're not going to be able to just rely on one definite integral notation to represent the full area of the regions that we want to find. So that means we have to think of this as two separate problems. We'll do top minus bottom for this left region, and then we'll do a top minus bottom for the second region. Both of these will give us separate answers, and then to find the full area, we're just going to add these two results together. Okay, so first thing I'm going to do is I'm going to find the boundaries by setting our equations equal to each other. So 3x cubed minus 3x equals to 0. I can factor a 3 and an x out. That leaves me with x squared minus 1. Continue factoring, that's the difference of squares. So notice that I have three separate x values, so I'm going to get three solutions. 3x will give me 0, x plus 1 gives me -1, x minus 1 gives me a +1. So these are the bounds, but notice that we have three values. Whenever you get three values, that's an indication that we're going to need more than one definite integral because of the multiple intersections that we're getting from these graphs. So we're going to set our, we're going to create two separate integrals, and they're going to alternate in the two regions. So for the first region, we're going to go from -1 to 0. -1 to 0. Our top function in the left region, as we draw our representative rectangle, the top graph, the top of the rectangle is sitting on the curve. That's the 3x cubed minus 3x. Minus the bottom of that region, which is going to be 0. That's the y equals 0. That's the x-axis. And then separately, we have integral from 0 to 1, top graph being the 0 now. If we look at our representative rectangle, the top of the rectangle is now sitting at the 0, and the bottom of the rectangle is sitting on the 3x cubed minus 3x. So we enter these in our calculator separately. This integral, definite integral, will produce 0.75. The second integral will give us the area of the region on the right, which is 0.75 as well. We add those two together, we get 1.5. So these two areas added together, 1.5 square units. Okay, number 8, find the area between the two graphs. We have the x minus 1 cubed, and then we have the x minus 1. Okay. Notice again, we have two separate regions. There's an alternating relationship between the top and bottom function. So again, just like example 7, we need to treat these like two separate integral problems with two separate areas, and then we'll total these up once we find them. So first we're going to find our bounds. Set x minus 1 cubed equal to x minus 1. I can divide both sides by x minus 1. I get x minus 1 squared equals 1. I do need to bring this 1 over to the left side because I can't set this equal to each other. I can't solve for x unless this side is showing a 0. So I got to subtract the 1 over. Well, first I factored out. I expanded out the x minus 1 squared. I subtracted the 1 over, and I get x squared minus 2x equals 0. Factored the x out. X times x minus 2 equals 0. I solve for x. I get x equals 0, 1, and 2. The 0 and 2 is from here, but the x minus 1, the x equals 1 comes from this x minus 1. If I divide both sides by x minus 1, anytime I'm dividing by a variable, I need to include that as a solution that I don't want to lose out on. So if we look at our graph here, our bounds are from 0 to 1 to 2. So 0 to 1 will incorporate the definite integral for the first region, and then 1 to 2 will incorporate the definite integral for the second region. Okay, so we set up our two definite integrals. First region from 0 to 1, the graph on top is the curve, that's the x minus 1 cubed. The graph on the bottom is the linear graph, the x minus 1. Again, make sure you protect that with the set of parentheses. Plus, second region from 1 to 2, but there's an alternating top graph now, right? The top graph has now switched to being the linear graph. The x minus 1 is on top now, and the one on the bottom is the x minus 1 cubed. Again, we put that in the set of parentheses. We enter this in our calculator, we get 0.25. We enter this in our calculator separately, we also get 0.25. We add those two regions together, and our combined area is 0.5 square units.